When you set out to build something, you usually want it to do something in the world. When you study engineering, you're learning a bunch of techniques that make you really good at making a machine perform some specific function. Generally speaking, your machine will need some kind of input from the world in order to do its job. If you're working with digital systems, which I do frequently, that means getting data from the world into a computer. This requires some kind of sensor or transducer, which converts a physical stimulus into an electrical signal. Right now, I'm opening the box to get a very special sensor system, my very own Microsoft Kinect. Why do I have one? Well, back in college, I had a friend working on a VR haptic feedback system who used one of these. I helped him a bit and got way too carried away and ended up buying myself one, only to end up throwing it in a box and letting it collect dust 2 or 3 apartments ago. But that ends today. I've got several projects in the pipeline that require depth data, and this is as good a time as any to get some work done. That said, how do I actually get data from it? My friend used Windows and Unity? I want to write C code and preferably use Raylib. I did some Googling and found out about libfreenect. A bunch of guys managed to reverse engineer the Kinect protocols and wrote a library to interface with it. So I switched to my Linux install, got that set up, and that didn't exactly work. I read some more documentation, uninstalled and reinstalled the library, and then got the example, protonect, to work. Great. The next step was to rewrite the example myself, which wasn't too bad, as I had the documentation and the protonect source code. The problem was compiling. I couldn't get the library linked correctly. After spending the entire weekend researching, testing, and failing to get libfreenect working, I tried this Azure dev library I had stumbled across, only to realize a few hours later that it's not for the Kinect, but some newer piece of Microsoft hardware. Running out of options, and quite frankly, patience, I decided to turn to Windows. They released a really nice SDK for the Kinect, and even though I'm not a fan of Visual Studio, I figured I could find a worthy compromise. If I could get Raylib working in C++, that would minimize the black boxiness of the coding environment. Thankfully, Raylib has a guide for using Visual Studio. While I had a tiny bit of trouble building Raylib, all in all the process was fairly painless. That said, I did run into some trouble when I tried including the Kinect 2.0 library into my Raylib project. There are a bunch of functions in the Windows libraries that conflict with Raylib functions. This confused me for a bit. Then I realized I could move all the Kinect stuff to a separate CPP file and link them together with a .h file, and finally got something working. I will admit that I initially tried to include the Kinect CPP file into the main, which just compiles the code in both simultaneously, resulting in the conflict. Including the .h file instead, and each CPP file is compiled separately, and then those objects get linked together into a working program, no conflicts. Anyways, I wanted to keep going now that it was working, but it was getting late, I was tired, so I set it aside and went to bed. Now that it compiles, all I need to do is take the Raylib documentation, the Kinect documentation, this OpenGL-based Kinect tutorial I found online, and Frankenstein it all together. Getting the color to work was pretty straightforward, and getting depth working wasn't too much more complicated. I didn't like how the distance was encoded into the colors, so I set up some demo areas for testing and started playing around with color schemes. The example I was referencing just modulused the depth value by 256 to get some value between 0 and 255, which could be written to the RGB values for that pixel, generating a grayscale image. This is a great starting point, but the modulus function returns the remainder of some division, and throws out the integer portion of the quotient. Since the depth value returned by the Kinect is a 16-bit unsigned integer recording the detected distance from the sensor in millimeters, you end up throwing out almost all the useful data that you really want in your program. So I played around with different methods of embedding the distance into RGB values. The Kinect accuracy supposedly caps out at 8 meters and also falls off around 4 meters. I figured the close-up stuff would be the most important, so I added a mapping function to map between 0 and 1 meter to the red channel, 1 to 4 meters to the green channel, and 4 to 8 meters to the blue channel, which almost worked. For some reason, all the close stuff was black. I went back to the docs and old forum posts. Apparently, the Kinect has an internal limit, and it taps out at below 800 millimeters. Anything between 0 and 800 millimeters is just registered as 0, hence the black. In need of a larger, or rather deeper environment, I ended up throwing this together. I also changed my mappings to be red 800 millimeters to 2 meters, green 2 meters to 4.5 meters, and blue 4.5 to 8 meters. I went to check everything and... Hold on, where's my measuring tape? How come I can never find it when I need it? This works, but doesn't look great. I beautified it a bit by overlapping the bounds slightly, which honestly is good enough. I implemented the linear mapping so I can get the raw data back out when developing for my future projects, which is the important part and all I really needed. And I really should have been satisfied with this and stopped here. But the next section sounded so compelling. This multi-day headache of a feature is actually pretty useful, if you're working on a project that requires it. And to be fair, most of my issues came from trying to render the output data, not in using the Kinect libraries that generated said data. A lot of applications that use this kind of depth detection technology will need to match the depth pixels data to the color pixels. And this is actually a pretty complicated issue. You can't just take a one-to-one mapping between images. First, they're different cameras, and the cameras are different sizes. The color camera is 1920 by 1080, and the depth camera is 512 by 424 pixels. No biggie, just stretch the depth image. But that doesn't work correctly because the cameras capture different fields of view. So you can do the math and figure out the color camera has a 22 by 20 pixels per degree, and the depth camera has a 7 by 7 pixels per degree. But there's a third and more significant curveball. The cameras don't occupy the same point in space. They're offset from each other, leaving you with a huge slog of trigonometry. Thankfully, the Kinect can do all of this math for us, generating a color pixel overlay that maps one-to-one with the depth pixels. We can use this information to recreate the scene in 3D using a point cloud, a bunch of points with XYZ coordinates and color associated with it. This usually uses GL points, which isn't supported by Raylib. On the plus side, Raylib has this feature where I can draw the 3D stuff to a texture and then just render that texture to the screen in the corner. At first, Raylib just crashed when I added the camera. When I fixed that, drawing small spheres seemed to ruin everything. For some bizarre reason, drawing 3D shapes in a loop caused everything in the 3D space to distort. So I shifted from that and tried using Raylib's height map function, which takes a grayscale image and generates a mesh from that. I spoofed the depth data into an image, and then, after beating it into submission, finally got something to generate and render. It doesn't look great, and there's a lot of craziness here because of noise in the Kinect's depth sensor. I was pretty interested in this feature, but I really just need the depth data, so this isn't a very big deal. Oh, there's one last and very entertaining feature that I wanted to play with. When my friend was working on his thing, the team had to get what they were doing with their body, namely their head and hand positions, into their application. That's why they were using a Kinect, which has full skeleton tracking. The device can track 25 joints on the human body and return that to the program via this big joint struct, which is pretty nifty. That said, the joint struct is part of the Kinect library, so I can't use it in my main graphics file. So I ended up just recreating the entire struct using Raylib types and wrote a big conversion function between the two. There are probably more elegant ways to do this, but the benefit of my method is that it's much easier to pass data into the Raylib's functions. For example, the Raylib vector 3 struct versus the Kinect location struct. It still took a lot of effort to convert the joint data into something renderable. First, the Kinect returns each joint position relative to the sensor, so I started by normalizing all the joint positions to be relative to the base of the spine. Then I created a big bones struct and implemented a function to convert the joint data into bones data. I probably should have made this structure a non-binary tree, but there are only 24 elements and it works, so it's not a big deal. By the way, here are the bones I created relative to the Kinect's joint indices. It was a little tricky setting up the body tracking and writing all the rendering code, but I got it working. Whoops, here's a cleaned up version. I wonder what this could be used for. On a serious note, if you look closely at the skeleton's bones, they jitter a lot. This is the same issue we saw with all that weirdness in the point cloud and the noise, but it's a lot more unsettling when you're looking at something human. We came up with some noise reduction algorithms way back when, but it's not an easy thing to resolve. I tried exporting my model to GLTF and GLB, which is supported by Raylib, and it looks mostly right in Windows 3D Viewer, but in my application it's horribly broken. I imagine this is an issue with the GLTF load in Raylib, which I read is still fairly new. A quick search and it looks like it might be an issue with applying transformations to the different pieces of my overall model when actually loading the GLB. They're all there, they're just not lined up. I guess I'll have to look into this system if I want to use my model at all. All in all, it's a pretty amazing little sensor system, and there are a lot of prototypes I plan to build with it, so we'll see how things go.